Okay, so it's 2 minutes past 2, and we are starting our colloquium today. Our speaker is Anna Malanusenko, whom we call Annie, and she will be speaking on the coronal veil. Annie earned her PhD from Montana State University in 2010. Her PhD advisor was Dana Longcock, and her thesis was on twist in solar coronal magnetic fields. Annie subsequently was a postdoc at Lockheed Martin Solar and Astrophysics Lab, working mainly with Carol Schreiber and Mark DeRosa on nonlinear force-free field extrapolations and on studies of solar coronal loops with the data from the just launched SDO. She came to HAO in 2014 as an ASP fellow, then became a postdoc and then a project scientist. Her major topics here are non-LT force-free fields, methods, work with Matthias Rempel on Muram data, which this seminar will be mostly about, and work with Sarah Gibson on several projects on interplanetary CMEs. Annie is excited to have recently gotten funding to continue both the Muram loop studies and the ICME studies. So I hand it over to Annie now.
Thank you for the introduction, Masumi, and thank you for having me here. Now, I will not be able to monitor the chat real time, so if you have questions, just shout out and I will address them. And with that, let's begin. The topic is the Coronal Veil, which is the title of the paper that is currently in review in UpJ with me and the primary author, and also Mark Chung, Craig DeForest, Jim Klimchuk, and Matthias Rempel. And it is a hypothesis, or rather interpretation, of the solar corona, more specifically of the emission that we see above the solar coronal region, active regions, that features those thin, bright strands that are called coronal loops. The coronal loops are typically thought to be a manifestation of hot plasma that is confined to magnetic flux tubes that is heated to just the right temperature so that we can observe it in whatever wavelength that we are looking through right now. And here is a comparison of the same active region. The left is extreme ultraviolet image, and on the right, the overlay is the blue and red is the photospheric, the surface magnetic field, and magnetic field lines. And as you see, the magnetic field lines do not identically correspond to the directions and shapes of coronal loops, but there's a certain resemblance. Coronal loops are arches that connect opposing polarities, and these magnetic field lines come from a rather simple model. So having said that, their comparison is stunning, and also there are physical reasons to believe this. The reasons are that in the solar corona, the plasma is what we call frozen in. That is to say, if a bit of plasma is bound by several field lines, so here's this bit of plasma, it is bound to move only between those two field lines forever. And also the heat is extremely well conducted along the magnetic field, but not across it. So again, if something hits the plasma between two magnetic field lines, everything between these two magnetic field lines will be effectively heated, but not so much across the field. Across the field conduction is non-zero, but it's thought to be much, much smaller. The hot plasma confined to magnetic flux tubes, and I mean, the intuitive picture for that is bar magnet and metal shavings, and something that we are very familiar with from high school to college physics classes. And this is intuitive picture, and it kind of allows us to treat coronal loops as essentially as a manifestation of infinitesimally thin, or not so infinitesimally, but thin nonetheless strands of plasma that generally follow the direction of the magnetic field. Now, once we think of it this way, there is a lot of good that we can do with this intuitive picture. For example, we can identify sometimes the same loop in different wavelengths. And then we can look at the intensity of a particular loop on our CCD detectors in those different wavelengths. And I mean, of course, this is a line profile. Of course, we will have to subtract the background, but then a loop would correspond to a bump, and the intensity of the bump will be different in different wavelengths. And the reason for that is different wavelengths are sensitive to different temperatures. And from that, you can do some math and figure out that from the ratio of the channels, we can infer the thermal composition of plasma inside this loop. So from coronal loops, we can, in principle, gather the physical conditions in the solar corona, such as temperature and density. Now, the same loop sometimes is seen as it evolves in time. And we can do the same analysis in different channels. And we can actually study how plasma in loops heats and cools. And this is important because the problem of why the solar corona is so hot is one of the cornerstones of modern solar physics, and we can address it by studying how coronal loops evolve in time in different channels. Now, there are less obvious or less traditional ways to study coronal heating with coronal loop images. For example, we can have models. We can have a magnetic model of an active region. We can insert plasma along the magnetic field lines according to different scenarios of the coronal heating and compare it against the observations. And from that, we can deduce whether a particular heating model is a good model or not. So this is a great way to test models of the solar coronal heating as well. Now, loops are finely structured. Then obviously the question is, what is the thinnest possible coronal loop? Do we resolve them? Is the resolution of our current instrument sufficient to resolve the thinnest possible coronal loops? Now, the reason why this is important is this is just to recall the frozen-in concept. The thinnest possible strands will tell us the thinnest possible spatial scales at which coronal heating operates. So that is another big open question. Now, there are magnetic applications. So given that loops are thought to be a manifestation of magnetic field lines, well, we can test magnetic field models. We can find magnetic field lines in different models that best match observed coronal loops. And yours truly has actually contributed to it. And my heart is in it so much that it is with great sadness do I exercise a self-restraint, and I'm not going to give a full-length seminar on just this topic right now because our topic is coronal veil, but I have a lot of work put into this particular application of studying coronal loops, and I feel rather passionate about it. From doing comparisons like that, I will just say that we can learn a lot about the coronal magnetic field. And again, this by no means is an extensive literature review, and obviously it's biased to what I personally think is interesting. But there are many other topics. So, for example, we can study how the tracks and footpoints of coronal loops change with time, and from that we can learn about solar flares. Or, for example, loops sometimes demonstrate oscillating motions, and we can study those oscillating motions. And we can model kink oscillations, and there is a lot of good math in there, but it's basically a very good probe for physical conditions in the solar corona. And I just recently came across this very, very nice review by Nakaryakov et al. 2021 on this topic. So we can learn a lot about the solar corona from studying coronal loops. And this intuitive picture is very, very useful. And coronal loops have been known for a long time, and they have been used a lot extensively. Again, I'm not going to, nor am I capable of giving an extensive literature review, but the concept of a loop as a manifestation of a thin magnetic flux tube is pretty much well one of the fundamentals of the physics of the solar corona as we know today. And my talk will be about an alternative hypothesis. And this hypothesis, as I hope I will be able to convince you, it's just as intuitive as the coronal loops hypothesis or interpretation. And the good part about the coronal veil is that it explains several things that are very, very difficult to explain with loops. There are some things that are difficult to explain with loops. Oh yeah, there are. So for example, magnetic flux tubes expand with height above the solar surface as magnetic field gets weaker. And if magnetic flux is conserved along the magnetic flux tube, then as the magnetic field gets weaker, the diameter of the flux tube should get bigger. And so if loops are basically magnetic flux tubes, then they should expand with height above the solar surface. And we do frequently see that the bundles of loops expand, but the loops themselves do not expand nearly as much as we think they should. Now, like I said, we could estimate conditions in plasma from studying intensity of loops with height. And for example, I mean, assuming, for example, that the plasma is in a hydrostatic equilibrium, we can apply analysis similar to what we do for Earth's atmosphere and estimate pressure scale height. And it's too high if we get it from loops. So loops are overdense, which I believe is the right term for it, but it basically means that they do not get dimmer with height nearly as fast as we think they should. There are other questions, like I did mention the question of their typical diameter. And the thing is that as the resolution of our telescopes increases, we see finer and finer strands. So there are some hypotheses on how to explain all of those. And those hypotheses are, for example, that there are electric currents in the magnetic field, and electric currents basically prevent magnetic flux tubes from expanding and force them to maintain a nearly constant radius. There is a hypothesis that loops are so thin we do not resolve them. So no wonder we do not see them expanding, that what we see as a loop is actually a bundle of loops. So there are hypotheses that loops form in certain places, for example. Or again, yours truly have contributed to this conversation by suggesting that magnetic flux tubes expand anisotropically. That is to say, if one foot point of a magnetic flux tube is circular in cross-section for the sake of the argument, this cross-sectional shape will not stay the same throughout the length of the magnetic flux tube. In other words, mathematically, the mapping that magnetic field provides between the two foot points is not in general conforming. I mean, if you look at the equations, there's absolutely no reason for it to be conformal. And so on and so forth. There are many hypotheses that explain that. But there is this coronal veil hypothesis that naturally explains all of those and more. So in order to go to the coronal veil, let's also go over the optically thin concept of plasma. And the thing is that given that we see throughout the entire solar corona, the images of individual strands overlay, and what we see is the composition of them, not unlike in this cutting-edge simulation, a shadow of this styrofoam bowl with little simulated flux tubes. So what we do see is this shadow. This is not by no means an extensively correct physical analogy, but it is good in illustrating the optically thin and the overlaid emission from a bunch of different sources. What we do see is the integral along the line of sight. What we do need to know to understand the true nature of these structures in the solar corona is the integrand. And the integrand is not something that we can study at present in the sun. We might need to launch a probe directly into the solar corona, possibly. Maybe there are other ways, but at present we cannot look into the depths of the actual solar corona. So we looked at a simulation. And this is the simulation. And in brief, it featured in Chong et al. Nature Astronomy. It is a Muram magnetohydrodynamic simulation extended into the corona. It features an emerging active region in the presence of an existing active region. And as is shown in that paper, it reproduces many aspects of the observations of actual active regions in the sun that we observe. That is to say, it's a really good simulation. It's one of the most detailed simulations of the solar corona to date. So we looked at it and we synthesized the emission from the simulation. And I'm showing here, I'm showing several solar active regions here in the context, just because this is an ab initio simulation. So it's not like there is a particular active region to compare it to. So this figure shows the simulation in the context of actually observed real solar active regions. So number 5 is the simulation, and all other figures are the observations of solar active regions. And as you see, there are many features that are similar, just qualitatively eyeballing. And again, the simulation captures most of the known physics. The simulation reproduces many processes observed in the sun. And as you see, the simulation results in realistic coronal loops. So let's study the simulation. Let's look at it in the volume. Let's study the integrand. And here's what I mean by that. In order to synthesize this image, I had to take the density and temperature cubes from the simulation above the photosphere. And there is a response function that takes into account atomic physics and all. And then I chose a line of sight, which is shown here by an arrow. And I basically calculated this function everywhere in the volume, density squared times the response function as a function of temperature in pixels in the volume, and then I integrated it along the line of sight. That is to say, the intensity in this vertical column of pixels on the simulated active region image is basically the result of the horizontal, in this case, integral of rows of pixels in the volume. So let's take a look at the slice of this integrand, or volumetric emissivity, and see what it has. Everything that I told you so far suggests that coronal loops are a manifestation of thin magnetic flux tubes, and there's a lot of good science that we can do with it. And in the simulation, we evidently see a lot of thin and bright coronal loops. So what will we see in this slice? Well, everything that I told you before suggests that we should see a bunch of isolated scattered dots in this image. And each dot would map into this integrated plane as a coronal loop. So here's the movie that shows both the integrated image in the backdrop, the volumetric emissivity, which is this moving plane, which is also a plane on the right. I also plotted several magnetic field lines. On the left, they're shown in 3D, and on the right, the diamonds show where they cross the moving plane. There are several things to notice about this image. One is that there are emissivity structures, indeed, in this plane, in the volume. Now, these emissivity structures are not thin and not compact. To be honest, I was expecting to see a bunch of scattered dots in this plane. Instead, what I see is something like clouds of smoke, perhaps a thin and wrinkled veil curtain. The features are so complex that it's hard to tell where one feature ends and the other feature begins. They merge and blend into one another. They have very, very complicated cross-section, and they're large. So in this particular frame, if I were to pause here, there would be several bright structures. And another thing to notice is that these bright structures are magnetic flux tubes indeed, because they do seem to be embedded inside the same set of magnetic field lines. And this is another important thing to notice. So there are emissivity structures, there are magnetic flux tubes. It's just that the cross sections of these magnetic flux tubes is neither thin nor it is compact. Now, it is certainly true that, I mean, there is scaling, there is display, and there's everything. So is it possible that only those brightest bits that you can say can be considered somewhat compact is what contributes to the image, and everything else is just background? And I mean, we do subtract the background anyway in the analysis of coronal loops. So to this end, we designed the following experiment. So again, I plotted several magnetic field lines. And as you see, the bright features in respective slices do seem to stay within this same set of magnetic field lines. I constructed these magnetic field lines by drawing intensity contours in the central slice, and tracing magnetic field lines from these contours. Well, how about I zero out everything else, everything outside of these contours, everything outside of this flux tube, and render the image and see what happens. And how about I change the value of the contour so that only brightest features remain, and see what kind of line of sight integrated image will I end up with. Well, I chose two regions on one of those two loop bundles from the simulation, region 1 and region 2. And here they are straightened out in a sense, and you can see the a certain picture of the coronal loops that are thin and long, and they overlay onto one another. And let's look at the emissivity in the volume. So this is a somewhat busy panel, but it's actually the essence of it is very simple. If you just look at the top row, the upper right image is precisely what I showed you before. The synthetic image a little slab extracted and straightened out. The left is the volumetric emissivity that is that maps into the middle, well, approximately the middle column of this pixel. Now let me see if I can draw here. So so somewhere right over here, if you look on 3D, this image belongs over here in 3D. This is a part of that moving plane that I showed you in the movie in the previous slides. And once you integrate this image along the line of sight, so along the line of sight, you will get intensity in this pixel in this column of pixels. Now I can zero out the dim emission and render the image, and I can progressively zero out more and more emission. Again, I zero it out in the middle plane, and I propagate. I construct magnetic flux tubes that contain the remaining emission, and I zero out everything outside of those flux tubes until only the brightest features remain. Oops, sorry. And the brightest features such as this. But as you see, if you try and compare the top and the bottom integrated volumetric emissivity, you will see that the picture of loops is markedly different. You see different structures. I mean, it is true that the image on the image in the bottom row is basically a subset of the image in the top row. So to get the image in the bottom row, I integrated a sub portion of the volume. So in the sense, this image in the bottom row is fully contained in the image in the top row, but it does not make the major contribution to the features that we observe. And here is, this is just a recall, which I also drew on the screen. And this is region 2, and you can see pretty much the same picture. There are a lot of coronal loops in the full image, especially here, for example, that are basically brought to existence by the dimmest features in the volume. And also the overall picture of the loop bundle changes quite a lot. And the moral of this exercise is that by removing dim plasma, we change the appearance of loops quite a lot. So in short, no, it's not only the brightest bits that matter. The dim emission matters a lot in the appearance of the loops that we observe. And the bright islands of emissivity by themselves are not enough to explain what we see in this synthetic solar coronal. Now, let's go back to this movie, and I will play it for a little bit just because it's cool, but also I wanted to pause it at just the right moment once the moving plane reaches the second loop bundle. So let's play it until just maybe right about, let's pause it right about here. And the reason why I wanted to pause it here is because there is a loop there that in the line of sight integral that we can study that is relatively long and isolated, and we can study it, and we can try and identify the feature in the volume that brought this loop into existence. So so roughly speaking, oops, sorry. Um, Roughly speaking, the image in this vertical column is brought to existence by the line of sight integral of this rectangle in the volume. So let's look at both a bit zoomed in. This is one loop, and to study it, I surround it with a curvilinear slab, and I take 6 slices across the loop. And in these 6 slices, I look at volumetric emissivity that I need to integrate to obtain the synthetic intensity in this synthetic emission slices images. So the top panels is basically the subportion of the synthetic emission, and the right panels are basically plane slices akin to this vertical plane, akin to the vertical plane and the volume of the volumetric emissivity. Note a feature here that kind of represents the archaic Greek letter kappa. And many kudos to Craig for educating me in archaic Greek. It really helped. It looks like this kappa shape feature is, as we argue in the paper, is what is responsible for the image of this loop. Why? Well, as you can see, and again, please bear off with me. It's a little difficult to explain in words, but it is really simple and intuitive. So in order to get intensity in the slices 1, 2, 3, 4, 5, 6, which are also plotted here. So those profiles are basically the intensity in the slices in the synthetic image. I had to do the line of sight, and in this case, horizontal integral of this rectangular subvolume. And as you see, there is a bump in each of those slices, and this bump is well, what we would call a cross section of a loop. Now, the dotted line here corresponds the same thing, but integrated in the subvolume. Okay, this was not a particularly pretty drawing on my end, but everything to the right of the vertical dotted line shown in these panels. And as you see, the dotted profile kind of resembles the solid profile quite a lot. So it is the integral of this portion of the volume is what is responsible for the appearance of this coronal loop. Now, there is a problem here. This feature is not quite compact. So this copper shape feature. And one thing to notice is that the loop is the most prominent in the locations where one particular portion of the copper is co-aligned along the line of sight. And in slices, say, number 1 and slices number 6, the loop is a lot less, the loop is not as well defined. But also notice that the bright portions of the copper are not co-aligned with the line of sight anymore. The second part is that the second part of the problem is that notice how the brightness changes in this one single structure. So in slice 1, the bottom leg of the copper is the brightest. In the middle slices, the horizontal bar of the copper is brightest. In slice 6, the top portion of copper is brightest. So copper should be taken, as we argue in the paper, as one big feature that rotates, changes in intensity, distorts in respective slices. So that is to say, it's not like we can just say it's not like we can just take the middle portion of the copper and say, well, this is our loop, this is our thin flux. We cannot really do that. We have to study this feature as a whole. And it does look like that this particular loop is a middle bar of a copper, or in other words, a wrinkle in a veil curtain, which gives the paper its name. Well, can stereoscopy help? What would this look like? What would this loop look like from different points of view? Well, I would argue that the stereoscopy would actually cause more pain than gain in this case, or more confusion, unless we figure out how to do it right. This is the portion of the volume that maps into the slab that we just looked at, viewed from different directions. And this one particular direction contains the loop we just looked at. But can you see the same loop in other viewing angles? No. But you will be able to see some loops. You might be tempted to say that some of them are our loop viewed from a different direction, but what are the chances that you will be right? And what are the chances that you will be wrong? Here is a different flyover of the same slab, just rotating it in a different direction. And this is its foot point. It's just the middle slice. The point here is that it really is the copper structure that brings a particular loop to existence along a particular line of sight. What happens if we have stereoscopy, such as the twin stereo satellites? And suppose, for the sake of argument, that they are in quadrature, that is to say, their lines of sight are 90 degrees from one another. So we have observer 1 and observer 2 looking from 90 degrees onto the same volume. Well, observer 1 would see two loops that correspond to two legs of this copper, roughly. And again, this is a conceptual hand-waving argument. Observer 1 would see two loops and the background in between them. And this background will be part of the feature itself. It will be the horizontal bar, the horizontal portion of the copper. Observer 2 would see one loop that corresponds to the middle portion of the copper, where the line of sight aligns with the particular feature, and it will see background around. Now, what happens if we subtract the background? Well, if we subtract the background, for the observer 1 would see this part as one loop and this part as the other loop. Observer 2, if they were to subtract the background, would only see this middle portion. So subtracting the background and isolating individual coronal loops in this case would actually subtract part of the feature itself. And this is just one feature. The actual simulation has many features. And if we have just two viewing angles, what are the chances that we will find the same loop that well, the same structure that manifests as a loop from two different viewing angles? And if you can try and follow individual features as this volume rotates, you will see just how difficult it is. And the question is it even possible? Maybe the third viewing point would help the situation. I do not know. That's an open question, really. Well, that is to say, the loops versus the veil hypothesis. Here's the second half of my cutting-edge styrofoam simulation of the sun. The classical picture of coronal loops is the picture on the left. The coronal veil hypothesis is the picture on the right. The simulation that we looked at seems to be in favor of the veil hypothesis. How can we tell them apart? That is a really big question. Now, the veil explains quite a lot of puzzles that I've mentioned earlier, such as, why do loops not expand with height if they are manifestation of magnetic flux tubes? Well, if they are optical artifacts, if they're caustics, of course they will not expand with height. And of course their observed pressure scale height will be too large. And of course, we will see finer and finer structures as we increase the resolution of our telescopes. Now, I would like to take a detour and talk about philosophy just a little bit. If you consider those two objects, which are garments from Earth, that have a purpose unknown to a group of aliens, these aliens, if they have absolutely no context, would struggle to reconstruct an appearance of an Earthling and would come up with interesting results. The point in this picture is that our experience shapes our interpretation of our future experience. And our prior experience is that with objects on Earth. And objects on Earth are a lot more often solid and palpable and, well, distinct, coherent. We're a lot less used to dealing with optically thin media. I mean, some analogies are perhaps puffs of smoke, maybe. But that's about it. I mean, most of the time we're used to objects like metal shavings and Bohr magnets. And our interpretation of what we see on the sun may be shaped by what we are used to perceiving on Earth. This particular simulation does not contain many compact loops. The paper that we wrote contains many more examples that show just how ubiquitous the veils are in this simulation. What about this active region? Does this active region contain loops, or does it contain veils, or does it contain both? And the million-dollar question is, how can we tell? Well, I would like to stress that it can be easy to take my talk as there are no loops on the sun, there are veils. This is not what I'm saying. What I'm saying is that we do not know if there are veils or if there are loops. We really need to think about it. We need to have a discussion about this as a community. And if we do any particular analysis that requires a compact shape of a loop, we must somehow make sure that we are looking at a compact loop. Well, enough of the philosophical discourse. I just wanted to point out that, I mean, the second typical comment that I do get when I talk about this is, what if MURAM is wrong? Well, MURAM can be wrong. Although, on the other hand, if you look at any single simulation out there, I mean, the arguments defending the simulation is that it contains known physics, it reproduces the observations, and MURAM is all of that. But the talk and the paper make a very strong argument. So I do acknowledge that this may not be enough in this particular case. So I just wanted to say that there are other studies that report similar effects like veils in different spatial scales, in different approximations in MHD and in non-full MHD even, such as Weinberger et al. 2014. So to my knowledge, the simulations have evolved to be genetically independent from one another. The only thing that they have in common is the physics that they try to approximate. And therefore, it must be physics that is bringing those veils into existence. That would be my point. Now, conclusions and implications. Coronal loops may appear due to a projection effect akin to wrinkles in the veil curtain. And the keyword here is may. That is very important. When studying a particular loop, this should be taken into account. The background subtraction may actually give us more trouble than it's worth. We may subtract a part of the feature itself. The most important topic is that some loops may be projection effects, and some loops may be compact, coherent, thin magnetic flux tubes. But how can we tell from observations? I just wanted to say, well, how do I personally feel about all this study? Well, I feel depressed because it impacts an unknown number of prior studies in ways that are unknown. I also feel excited because in order to work with veils, if we proceed with this interpretation, we will need to develop a completely new set of image processing algorithms, a completely new set of models, a completely new set of math, perhaps. And I'm looking forward to seeing what these methods will be. But also new methods typically bring breakthroughs in our understanding of physics. And I'm also looking forward to this very much as well myself. And that is to say, this is not something that I can do on my own. This is something that we need to work on as a community. There's got to be a lot more minds behind this, thinking about this. There is a lot more than I can think of on how to deal with this. Well, does it mean that I've given up? No, no way. I only just started to have fun. And I just want to, I have a couple of minutes, and I would like to show a couple of slides from one way of attack that I'm going to pursue in the near future to see whether okay, the first $1 million question is whether we're looking at whales or whether we're looking at loops when we see a particular active region on the sun. So also, this will be just 3 brief slides, and I will talk about it in more detail in the upcoming AGU meeting. But I am extremely excited in that our team won a funding proposal to pursue this project. And the project is to address this problem statistically. So if you look at this particular active region on the sun, and I just took a middle slice through the loop tops and counted 18 local maxima in this particular case, and 18 loops. Are they 18 loops or are they 18 projection artifacts? Now, that is the question. I do not know if I'm able to discern a particular feature just by looking at it just like that, but maybe we can look at the problem statistically. And here is how. And this is a super simple illustration. We are just starting with this project, and again, this is just a conceptual illustration to show what it's all about. And this is a bunch of coronal loops from a dipolar magnetic field, potential dipole loops that are compact strands. In this case, isothermal, hydrostatic. Again, I'm just focused on features. And my point is that the statistical properties of these features would depend on the volumetric emissivity properties. So again, the synthetic emission in the left, the image in the middle is similar to what I showed you in NEROM, but the line of sight now is looking top down at an active region, and the emissivity slice showing a bunch of scattered dots as a standard interpretation of coronal loops. Well, how about different interpretations? So we can look at one large structure with complex edges, or we can look at just the edges themselves, so wrinkles in the veil, so to speak. And the argument is that those 3 cross sections will produce statistically different characteristics of the image, such as the total intensity and the total loop count. So if you compare the synthetic emission based on these 3 different emissivity profiles, you will see that the image on the left has a lot less background and a lot more fine structure. The image in the center has a lot more background and a lot fewer loops. And the image on the right is somewhere in between. So if we just plot the number of loops versus the total intensity, in this particular case in the middle slice, you will see that I generated a gazillion of those and at random, and I studied the dependency and this super simple model, and it does look like they can be described by this relationship can be described by a power law. The number of loops is proportional to the total intensity to some power, and the question is, well, what does it look like in the real sun? And we got a project to pursue this statistically and also with neural simulations. And at that, I end, and thank you for your attention, and I'll take questions.
Thank you, Annie, for a very nice presentation. And now it's open for questions.
And there are some questions. Ryan Hoffman, depressed because I want to know things in the universe says no, story of my life. Well, but also excited because we're looking for the breakthroughs here. And I mean, what was my aspiration when I realized that I wanted to be a scientist? I wanted to discover the unknown. And here it is, this unknown. It's looking at me, it's grinning at me, it's waving its hand at me. It's right in front of me. All I need to do is to figure out how to handle it.
So Anna, this is Joe Plowman.
Mm-hmm.
It seems to me that this doesn't necessarily rule out the idea of loops per se, but it rules out a kind of a reduced subset, which is that they're kind of thin and simple structures that are sparse on in the volume of the corona, but instead that they're instead they have to fill the volume, and in some parts their shape may be more complicated. I think you can still match a lot of what you showed with using a set of loops as a basis, if you know what I mean. It's just that the kind of that earlier paradigm is a little bit too restrictive.
Yeah, I do tend to agree with you. In fact, I'm just going through this. Yeah, you can say that what you see here is a combination of of everything. There's a combination of diffuse big structures. There's a combination of little compact things, and there is a combination and there is some component of sprinkles in the veil sort of thing. And actually, the same is true. I'm going to go to the slide that shows different other studies. I mean, they're not as detailed and complex as Muram in particular. Weinberger et al. 2014, but it illustrates it excellently what you just said. There is a combination of compact strands, which are a subset of what we see. There are diffuse structures, and then there are veils.
I say this in part, of course, because I have some work that uses volume filling loops as a basis for modeling observed emission, and it seems to work pretty well, actually.
Okay.
I have a paper on that out in the archive. I welcome people to go look it up if they want. It should be published in AppJ pretty soon.
Thanks, Joe.
Vic.
Yeah, I want to make a comment about, you must be familiar with the idea of caustic surfaces as espoused by DeForest and Howard, right?
Yep.
Okay. Which has to do with the idea that suppose you have a loop that's actually quite, where the density is restricted pretty much to the edge. And then you look through that in a 3D sense, and so you look at where the density piles up the most. Well, it's on the very edge of those loops. And the picture you get of a corona composed of those things is very, very different than you would get of the versus a conventional loop picture that most people think of. And it's optically very confusing what you're looking at as a bottom line, and it's you can't interpret it very simplistically. You're seeing edges only, and you have an infinity of edges basically in the corona because you got loops all over the damn place, and so that's another way of viewing this. And unless the loops actually have a fair amount of density inside of them, then you'll get more closely to that caustic picture than you will to what most people think of as a constant volume loop or a loop with a constant density across the whole volume or something.
I was scrambling to see if I can find this paper in a haste. Did you mean this paper?
Yeah, I don't have it offhand, but
you still see my screen, right?
yeah, I can see the screen.
So
yeah, and they studied a number of different situations and kind of what would you see if that were the case, and it's extremely surprising what you see. I mean, it's not what you think you would see, you know, in firsthand.
Yes.
And the second question, I guess, is what do they do in the model that you were talking about there that underlay a lot of these, what you were showing? How do they assume density is distributed within the loops? Or how is it actually distributed?
Yes. I mean, I don't have anything else to say to that than yes, absolutely.
Okay, so I mean, this is part of this whole coronal thing. Anytime you look at line of sight integrations, even out further in the corona, not down low, but looking at CMEs and stuff, it's extremely complicated, and most people don't really understand how complicated it is and how many situations you can get yourself into. That I mean, sometimes there are things that are pretty straightforward, but other times it's not, and it's just a very difficult problem. That's all, to put it simply.
It is, and it actually doesn't. It's not restricted to solar physics. Actually, I found this paper by Hester in 1987 that regards supernova remnants, and it's actually interesting to look at. So they interpret astrophotography such as this, and astrophotography such as this, and they try to explain it with actual photographs of their actual mesh screen. So this is actually the window mesh screen actually photographed, published at UpJ. So it doesn't only plague solar physics, but rather, I mean, everything where optically thin stuff exists.
Yeah, it's a generic problem with if you can see through something, it's optically thin and all. It's just very tricky.
Mm-hmm.
You have to know kind of what's going on at the source, so to speak, and you have to make an assumption that to really come to any conclusions.
The big advantage in this case is we know that the magnetic field structures what we're looking at a lot, and we know that the magnetic field only can have certain configurations. So I think that's one of the big levers that we can lean on.
But we still think about magnetic, but we still think in those infinitesimal increments which are thin, you know, magnetic field line. Well, this is a wonderful concept until you surround it with a thin magnetic flux tube. But this flux tube, I mean, it gets deformed so much. If you just take any model of magnetic field and just follow a flux tube from the beginning to the end. And I'm not talking the high Q regions even. I'm talking about just general. I mean, I guess it's one place where our perception plays tricks on us.
Okay, next question by Ryan and then Kevin.
Hey, so great talk, first of all. This is kind of, I guess, related to the last question. The question of veils versus discrete little flux tubes. What determines whether you get one or the other physically? Like, why does your neuron simulation show these long, complicated, folded, connected structures, or something more compact? Like, and also related to the last remarks about the CME projection stuff. Like, are we seeing bubbles? Are we seeing actual dense, bright cores? Like, physically, what's going on with the with making veils versus isolated like loops?
I have a thought, and at least one part of a thought. By no means it's extensive, but I'm just going to take a screenshot of this Weinberger 2014 paper because again it's a really nice illustration of one particular concept. Control V. Oh, it doesn't insert. Okay, anyway, I'm gonna have to draw. So the thermal response function is narrow in some channels, in such as 171. And here's what it boils down to. Suppose that you have, I don't know, X, and suppose that you have a distribution of density of plasma as a function of X, and suppose there is a bump here, okay? Suppose also that you have a distribution of temperature along in the same region, and again it's also a bump for the sake of argument. Now, given that the thermal response functions are narrow, when we plot the emissivity, which is how much plasma is bright in a particular channel as a function of X, what we'll actually see is too thin. Is basically the isoline of constant temperature for narrowband channels, and here we have veils. So that is one immediate explanation you can think of.
I'm sorry. When you say that the temperature, that the temperature response or whatever is very narrow, maybe I'm not fully understanding what that means. Like, how do you go from two overlapping bumps in these different properties to a double peak emissivity?
Yep. So so we know from our atomic physics that okay, this is probably not the best color. We know from atomic physics models and some other telescope optics. I mean, okay. Anyway, we have some models that say that a plasma at a temperature T emits a certain amount of light in a given wavelength. And the plasma at a different temperature emits less light, and a plasma at a yet different temperature emits less light, even more or less. I think I might have actually some of those plots for AIA. So the x-axis is the logarithm of temperature, and the y-axis is basically how much light would be emitted by a chunk of plasma heated to this temperature at this particular wavelength. And this is that response function R of t, and then to get the emissivity, you need to multiply it by the density squared, and then to get intensity, you need to do the line of sight integral of the emissivity. Yes. So something like that. That makes sense. Now, those response functions for some wavelengths that are pretty narrow. So I wonder if those thin sheets in Weinberger et al. 2014 are just isolines of constant temperature in a way.
So I have some comments I can make on this if you want.
Yeah.
So kind of going along with your point, if some of these channels, like say 171, only respond to material at around 800,000 Kelvin. So if the loop goes way above that temperature, it'll get dim again, and you won't see it further up. Another point is that in those cooler temperatures, the radiative cooling time is much shorter than it is at the higher temperatures. So effectively, in the higher temperatures, you're seeing a longer time averaged kind of slice of the heating that's going on in the corona. And so the material will tend to look more diffuse because it's a longer dwell time.
Good point.
And in some of these cooler channels, you'll see sharper features because you only see stuff that's just been heated or that's just recently arrived in that particular temperature range. The last point is that because, so what you said towards the beginning of the talk, that heat conduction and transport along the field lines is very efficient. If you bang on a field line with a bunch of heat, and you do it in a very localized place in the transverse direction, so it's just a small sized heating event there, then you will see just that loop effectively light up, and the rest of it won't. But if the kind of the heating event that's going on is kind of more distributed, then you'll see a more broader part of the corona light up, maybe with some of those more complicated structures that you showed.
Oh, I agree with everything you said, especially with that, we do actually observe that more diffuse features in some channels, and coincidentally, yeah, and those channels have these properties. I'm just trying to remember how I did this exercise with AIA, and they just tracked the same active region for a long time, like several hours when it was in the disk center, and I did the time averaging, thinking that, well, I got to get some diffuse structures. What I got after doing a long time averaging was still a nice and crisp feature images of coronal loops. And yeah, I mean, I encourage people to repeat this experiment. It's fun. I mean, the image is fun. So yeah, there are questions in the chat. There are questions in the chat, and I apologize.
Kevin has a question, and then there are questions and comments in the chat.
Yeah, I had a comment and a question. So one is that we've, posited a very similar sort of structures in the chromosphere as well, right? That we can explain some of the, collinear features, the spicules and so on may be similarly just a line of sight effect that we're seeing through a corrugated curtain of magnetic field. So I think that, it's an interesting that, see this in the corona as well. My question was, would there be any difference in the heating rates you might see in the case where you have these, mostly aligned magnetic fields, and the sort of that the loops indicate, a loop interpretation would indicate are all sort of are fairly regular compared to, the much more complex magnetic field structure you're seeing in Muram, where you might have more tangential discontinuities and different sort of heating profiles in the corona. Is there any way to distinguish by looking at those, heating rates and event sizes?
So the answer is yes. That is to say, yes, that is a question. I do not know the answer to this question, and I would like to know it.
So Annie, could you see all those chat? There are comments and questions.
Yes. So fire is kind of similar, and that is true. That's cool. The heat and cooling might contribute to the selection of loop veil structures. Yes, yes, very much so. And I'm just so happy that people are giving such a good ideas and thoughts, and there's a discussion out loud. One also has to account for the instrumental effects. Oh yeah, absolutely. And the optically thin spectroscopy with non-equilibrium ionization is super interesting too. And yes, it is interesting. And it's one of the topics I do not know much about. I do not know as much as I would like to know. So yes, which is why I'm very, very happy to have a community conversation on this. And Should a flux tube be able to contain plasma anyways? And are there physics that we know that would enable, disable confined plasma? I do not know.
Just to say that out loud, it's like, okay, we talk about a flux tube being filled with hot plasma, and I guess magnets are involved, so it probably can be held in, but like, is there a very clear, like, well, if you have this magnetic configuration, that should generate a closed, like, flux tube that confines plasma? I mean, I know that we kind of see evaporation at loops and then condensation back down, but I just don't know if we know anything that should push us towards that's more likely to occur than a veil or not.
See the next comment, Sarah has a comment on that.
Yeah, actually,
Why?
Gilly, your comment was what remind me of the work that Paul Bellin does at Caltech. He does laboratory experiments combining plasma in loops and has some interesting thoughts about. He has some papers and some more recent work. Actually, this was back in 2003 with the loop cross section, and it had to do with helicity injection. But anyway, I had to put this particular one up because of the gobbling up plasma.
Sure. So the bottom line is there is some reason why loop.
There can be, whether it's relevant for the corona is, I think, the question that is interesting.
Cool. There's a lot of math in this one.
To my embarrassment, I cannot clearly answer. I cannot answer Noir's question about the collision-dominated regime off the top of my head without some thinking and reading and thinking some more. So this is something that I will need to address later, perhaps in an email after I thought. And I thank you for this question because it's something I should know, but off the top of my head I do not. And then there is another Gilly, another reference from Gilly, collisional versus radiative plots in the end of 2020 paper.
Yay!
So,
First getting pulled up.
Page 26.
I think. Yeah.
So I would assume it's something very last.
I think that's actually the paper Sarah was just mentioning.
Oh.
Yeah, it's worth, and there's some stuff that Gordon Petrie worked on too, which was related, and so there were some interesting debates on this at the decade and a half ago. So anyway.
Mm.
There you go.
Mm.
So that's kind of showing around one solar radii above the surface, depending on the wind strength is what the different lines are, but it turns out that a lot of lines can be relatively radiatively dominated above around one solar radius over the limb. Just a data point.
Thank you. Well, thank you very much. And guys, thank you for all these comments and thoughts and ideas and questions. And thank you for listening.
If there is no other questions, let's thank our speaker again, Annie, for a very exciting